The fundamental theorem of calculus, part 1. Generally, the fundamental theorem of calculus is divided into two parts. I'm going to call this first part, part 1. If f is continuous on some closed interval ab, and I define a function, capital G of x, to be the integral from a to x of f of t dt, then that function, the capital G of x, is also continuous on the closed interval ab and differentiable on the open interval ab. And the derivative of g of x is equal to f of x. In other words, if I differentiate this integral, I just get this function back. I get f of x when I differentiate this integral with respect to x. Now, before we proceed with the proof, let's consider a function f, and let's suppose that it is differentiable, or let's suppose it's continuous on the integral from x to x plus delta x, and let's suppose it's differentiable on the open interval from x to x plus delta x. And let's suppose that we integrate this function. Now, if we integrate this function, what we would get is the area under this curve, the area bounded by this curve and the horizontal axis. Okay, now, the extreme value theorem tells us that when we have this kind of function that's differentiable, or that's continuous from x to x plus delta x and differentiable in the open interval, it tells us that there is a u in that interval such that f of u corresponds to a max, and there's a v such that f of v corresponds to a minimum. So we have a u and a v in this interval. And let's do this. Let's say that we want to approximate the integral, which is the area under this curve, by a rectangle. And let's suppose that the width of that rectangle we'll use to be f of u, the maximum. And of course the length is delta x. Well, that would give us the area of this rectangle, which is more than the actual integral. So we would say, okay, the integral is less than delta x f of u. And then we could go the other way. We could say, okay, well, then I want to use the width of the rectangle to be f of v, which is a minimum. And the length would still be delta x. But in this case, you see that you have a lower estimate. And delta x f of v is less than the integral. Okay, so keep that in mind as we proceed with the proof. Let's define a function g of x to be the integral from a to x of f of t dt. And we'll say that x and x plus delta x are both in this interval a to b. Well, let's find the derivative. To find the derivative, we go back to the difference quotient. And here is applying the difference quotient to our function g of x. Now, I'm going to go ahead and put in the integrals. So I'm leaving the g of x and now putting in what g of x equals. And now you notice that in place of x, I've put x plus delta x here. And then over here, I'll just leave the x. Now, I want to do this. I want to, instead of integrating from a to x, I want to change it and go from x to a. Now, I can do that as long as I change the sign out front. So this difference quotient here now looks like this. Notice, instead of going from a to x, I'm going from x to a, and I've got a plus instead of a minus there. Now, if that's the case, what if I do this? What if instead of having x to a and then a to x plus delta x, what if I just combine those into this one integral, where I'm going from x to x plus delta x? So now I have something that looks a little bit less complex. I still have the same limit, everything's the same, just looks a little bit less complex. Now, let's put into play what we talked about a minute ago with the extreme value theorem, and we'll go back to our u and our v. We know that this integral, Now notice the delta x is not in front of the f of v or the f of u. It's down here in the bottom of the integral. It's as though I divided it out. But the fact is that this integral, the integral from x to x plus delta x f of t dt over delta x, is between f of v and f of u. Now, let's think about what would happen if delta x goes to 0. Well, if delta x goes to 0, that's the same as v going to x of f of v, and that's the same as u going to x of f of u, and that just equals f of x. So what we're saying is that the limit of f of v of this left and this right, they're both going to f of x. So what happens then is this thing in the middle gets sandwiched in. So by the sandwich theorem, we have this, that the limit as delta x goes to 0 of this thing is equal to f of x. Now what is this thing? Well, the limit as delta x goes to 0 of f of x, the limit as delta x goes to 0 of the integral from x to x plus delta x f of t dt over delta x. Remember, we got that from the difference quotient. In other words, this is what the difference quotient simplifies to. So what we're saying is the limit of the difference quotient is equal to f of x. In other words, f prime of x is equal to f of x. This is precisely what we want it to show.